We're going to start with axiomatic probability, probability from the axioms. Now, in addition, there also is often more than one variable. So we may have two variables associated with the same set. Or more rigorously, given a sample space, we'll look at a new sample space of pairs of outcomes from the original sample space. For example, a pair of dice rolled simultaneously, X would be the outcome of the first, Y is the outcome of the second. Two players dealt cards from the same deck, each playing a card simultaneously. X and Y are the values of the first and second player's cards. Or perhaps we may actually just define our sample space to be pairs of outcomes. So this is a subset of R2, and we'll still consider this to be a numerical sample space. X and Y are variables associated with S in the sense that a trial of X paired with Y is of the form T sub X, comma, U sub Y. For example, a square on a chessboard chosen at random from row X and column Y, or a 6-sided die and an 8-sided die are rolled simultaneously. X and Y are the outcomes of the dice respectively. In general, sample spaces, therefore, are numerical in that they're subsets of Rn, and the tags are vectors in Rn. So let's look at some notation. Our sample spaces are going to be finite subsets of Rn, and that means we'll have tuples of variables indexed by the lowercase. An important example is two variables. The probability that capital X is little x and capital Y is little y. It's the probability of the outcome tagged by T sub X and U sub Y. This is called the joint probability distribution, often written in the lowercase probability of X, Y, which is the outcome indexed by little x, little y. So continuing with this same sample space, joint probability as we saw previously, the marginal probability of capital X is the probability that capital X has a value little x, given that y can take on any value. And we can make this rigorous by defining E sub x, where T sub x is the same, and then you have variation across the second coordinate. E sub y is similar. So the marginal probability of little x is the probability that xy is in little e to the little x. And similarly for the marginal probability in y. That means that the marginal probability of little x is the sum over these y's of the probabilities, and the same with the marginal in y. Let's use a little better notation. So when we say y equals y, we really mean y equals u sub y. So that means we have a sum of y equals 1 to q. Similarly, x equals x is actually notation for the idea that x equals t sub x. And we often just let the index variable indicate the marginal probability. Joint probability. Let's suppose that Dr. Yu in China and I in the USA both flip fair coins at the exact same time. Capital X is my outcome, capital Y is Yu's outcome. These are the four possibilities. This is my sample space. Each possibility, each outcome has a probability of a fourth. So a trial is heads for me and tails for you. Each outcome is equally likely, so the probability that XY is heads tails is 1/4. In function notation, we write P of 1, 0 as 1/4. Marginal probability, same example, same sample space. The marginal probability of 1, I sum over where the y's vary, but the x's are fixed at 1. 1/4 plus 1/4, that's a half. Probability of heads for me. And the marginal of 0 is similar. A half, that's the probability of tails for you. Again, if careful, we can use P of X and P of Y, the index or the notation for the argument, to tell us which of these marginals we're using. So P of X is a half for me, and P of Y is a half for you. So joint probability, if A is a subset of S, then it's equal to some collection of tuples, which we can denote using these permutations or rearrangements. And again, if we say XY is in A, we mean that the pair T sub X and U sub Y is in A. So the probability of A is the probability that XY occurs in A, which is the sum over XY and A of P of XY. And now we can use all the usual set concepts. The probability of the intersection is the sum over the indices in the intersection, P of XY. Sum of the union similarly. Probability of the union similarly. A new notation, B prime, we're going to call all the outcomes in S that are not in B. And this leads to the very important concept that the probability of B prime is 1 minus the probability of B. We often get our probability distributions also from data, which is called an empirical distribution. So let's look at an example. So suppose, just for illustration, that 1,000 students were asked to choose their favorite college sport. So our raw data is just the counts, and we divide each count by the total number of students, 1,000 in this case, get probabilities. The capital X variable is gender and the capital Y variable is sport. And we use numerical indices, as you can see here, instead of the names of the actual sports and genders. So suppose a student is selected at random from the 1,000 surveyed. What's the probability that a student is male with a favorite of basketball? Well, we look at our numerical tags and see that we're looking for the probability of 0, 1, and that's 0.15, male and basketball. Probability the student is female with a favorite of softball, that's in the baseball softball category. That's a P of 1, 2, and that's 0.20. Our marginal probabilities for X is just the sums over the row, so there's a 50% chance of male and a 50% chance of female if you were to select a student at random from this 1,000 students. Similarly, we get the marginal distribution for Y. If we have this event A, which is male, and favorite is not other, then we're looking at male in football, basketball, or baseball. The probability of that event is the sum of these three probabilities, which is 0.45. The probability of event B, which is favorite is not football, all of these, well, actually it's independent of gender, so we really only need to look at the marginal distribution in Y. And the sum of all of those is 1, so we really just need to take 1 minus the probability of football, and that's 0.65. So let's look at conditional probability for a variable x versus variable y. So recall the definition of conditional probability and joint probability. We're going to define the set E sub y, as you can see here. All the second coefficients are the same U sub y. In other words, this is a condition of y is U sub y. So we look at the probability of A, given that y is U sub y. B is equal to E sub y, so that means we're going to be taking A intersect E sub y. The probability of B is the probability of E sub y, but that's the probability that y is U sub y. So we put that there, y is U sub y. And if we let A be e to the sub x, then notice now all the first coefficients are t sub x. What does that mean? That means the probability that x is t sub x, given the condition y is U sub y. And A intersect E sub y is just the single t sub x U sub y. And that's the joint probability. So we have the joint probability. The denominator is the marginal probability with respect to y, and therefore we get this formula for conditional probability. So let's go back to our empirical example. Let's consider this example of the probability that x is female given that y is football. It's probably x is 1 given that y is 0. That's the joint probability of 1, 0 over the marginal of 0. We can see those values here. So that's 0.1 over 0.35, 27 is about 0.286. Let's do another example. Let's look at the probability that x is male given that y is other. It's probability that x is 0 given that y is 3. And that's the joint probability of 0, 3 over the marginal of 3. And notice that the probability of being female and other is 0. So therefore, the values that we have to use to calculate are the same. In other words, probability of 1, a conditional probability of 1. So let's look at another example. This event male and favorite is not other. We can see that. And favorite is not football for our event B, and those are the values corresponding to that event. So we want to look at the probability of A given B, which is the probability of male and favorite is not other, given that, conditioned upon, we know that their favorite is not football. Independent variables, let x and y be associated with the same set. Remember, those are numbers. The joint probability is the probability that x is t sub x and y is t sub y. And if p of x condition y is equal to the marginal probability of x for all x and y in S, then the variable x is independent of the variable y. So here's our definition of conditional probability. There's our definition of independence. Notice that p of xy is therefore the product of the marginal distributions of x and y respectively. Notice that x is independent of y only if y is independent of x. And the variables x1 to xn associated with s are independent if xi is independent of xj for all I not equal to j. So in summary, multiple variables is when we have a sample space that's a finite subset of Rn. Outcomes are variables over S in Rn, indexed by lowercase x1 to xn. Two variables was a very important example, and going forward would be important. Joint probability, probability that x is x and y is y, is often written P of xy. Conditional probability that x is x given y is y, that's a probability distribution for x where y is constrained to be use of y. An important result we just touched on is the concept of independent variables. Independent variables are very important in sampling and also in modeling because we have this joint probability distribution is the product of the individual probabilities. We'll see this quite a lot going forward.